this video, we will discuss some key properties of carbon, as well as how to calculate degrees of unsaturation for hydrocarbons and other simple organic molecules. A carbon atom has 6 total electrons, with 4 of these electrons in the valence shell. As a result, we refer to carbon as tetravalent because these electrons can participate in bonding, allowing carbon to form 4 covalent bonds with other atoms. A carbon atom bonded to 4 other groups has a tetrahedral geometry with bond angles of approximately 109.5 degrees. To draw a tetrahedral carbon center, we first draw 2 bonds on the plane of the paper like this. A wedged bond indicates a bond pointing out of the page or towards us, and a dashed bond indicates a bond pointing into the page or away from us. Tetrahedral carbons are often drawn without stereochemistry for simplicity, but it is important to keep the tetrahedral geometry in mind. Now let's take a look at some simple organic molecules. Much of the carbon we encounter in organic chemistry is in the form of hydrocarbons, organic compounds consisting only of carbons and hydrogens. While there are many different types of hydrocarbons, they all fit into 2 big categories: saturated and unsaturated hydrocarbons. When we say a carbon is fully saturated, we mean that it is bonded to the maximum number of hydrogens possible. For example, propane is fully saturated, as each carbon is bonded to the maximum number of hydrogens possible. Meanwhile, propene, or propylene, is unsaturated because the 2 double-bonded carbon atoms are not bonded to the maximum number of possible hydrogens. In a fully saturated hydrocarbon, the number of carbons and hydrogens is related by the formula CnH2n plus 2. This class of hydrocarbons is referred to as paraffins, but is more commonly known as alkanes. Alkanes on their own are typically non-reactive and are characterized by having only single bonds between carbons. They are also denoted with the suffix -ane, as in methane, ethane, and propane. In unsaturated hydrocarbons, each multiple bond or ring reduces the hydrogen count by 2, which we refer to as a degree of unsaturation. We can calculate a molecule's degrees of unsaturation from its molecular formula using the following equation. Degrees of unsaturation equals 2C plus 2 plus N minus H minus X all over 2. In this equation, C equals the number of carbons, H equals the number of hydrogens, N equals the number of nitrogens, and X equals the number of halogens. It's important to note that this only tells us the sum of multiple bonds plus rings in the molecule as a whole, but not exactly how many multiple bonds or rings are present. Alkanes have 0 degrees of unsaturation as they are fully saturated with no pi bonds or ring structures. Molecules with 1 degree of unsaturation contain 1 pi bond or ring structure. In these hydrocarbons, the number of carbons and hydrogens is related by the formula CnHn. However, there are no stable molecules of the CnHn family with the formula CH2 for reasons we will discuss in a later lecture. Hydrocarbons that contain carbon-carbon double bonds are referred to as alkenes. Alkenes are more reactive than alkanes and are denoted with the suffix -ene, as in ethylene and propylene. Hydrocarbons with 3 or more carbons can also be drawn as ring structures, such as cyclopropane, cyclobutane, and cyclopentane, which are 3, 4, and 5-membered rings. Molecules with 2 degrees of unsaturation fall into 3 broad categories and can contain either 2 pi bonds plus no rings, 1 pi bond plus 1 ring, or no pi bonds plus 2 rings. In these hydrocarbons, the number of carbons and hydrogens is related by the formula CnHn minus 2. Let's take a look at the first category, 2 pi bonds with no rings. Hydrocarbons with carbon-carbon triple bonds are referred to as alkynes. Alkynes are denoted with the suffix -yn, such as in propyne, and have their own unique reactivity, which we will explore towards the end of the lecture series. Alternatively, a molecule can have 2 pi bonds in different locations within the molecule or between 2 different pairs of carbons, such as in dienes like 1,3-butadiene. Structures with 1 pi bond and 1 ring are called cycloalkenes, such as cyclopentene. And finally, structures with 2 rings are called bicyclic compounds, such as this molecule here. A molecule isn't limited to only 2 degrees of unsaturation. It can have 3, 4, or more degrees of unsaturation, and the same rules apply. For example, hexatrine has 3 degrees of unsaturation, and benzene has 4 degrees of unsaturation. Let's do some practice. Calculate the degrees of unsaturation for the following molecules given the molecular formula. Feel free to pause the video and try these problems on your own first. We can calculate the degrees of unsaturation for each of these molecules using our formula. In C2H4O, there are 2 carbons, 4 hydrogens, and 1 oxygen, but 0 nitrogens and halogens. Plugging these values into our formula, we get the degrees of unsaturation equal to times 2 plus 2 plus 0 minus 4 minus 0, all over 2, which gives us a final value of 1. Hence, we can conclude that the molecule has 1 degree of unsaturation. In C5H14N2, there are 5 carbons, 14 hydrogens, and 2 nitrogens, but 0 halogens. Plugging these values into our formula, we get the degrees of unsaturation equal to 2 times 5 plus 2 minus 14 minus 0, all over 2, which gives us a final value of 0. Hence, we can conclude that the molecule has 0 degrees of unsaturation. In C6H10, there are 6 carbons and 10 hydrogens, but 0 nitrogens and halogens. Plugging these values into our formula, we get the degrees of unsaturation equal to 2 times 6 plus 2 plus 0 minus 10 minus 0, all over 2, which gives us a final value of 2. Hence, we can conclude that the molecule has 2 degrees of unsaturation. In C5H5N, there are 5 carbons, 5 hydrogens, and 1 nitrogen, but 0 halogens. Plugging these values into our formula, we get the degrees of unsaturation equal to 2 times 5 plus 2 plus 1 minus 5 minus 0, all over 2, which gives us a final value of 4. Hence, we can conclude that the molecule has 4 degrees of unsaturation. Finally, in CH2Cl2, there is 1 carbon, 2 hydrogens, and 2 chlorines, but 0 nitrogens. Plugging these values into our formula, we get the degrees of unsaturation equal to 2 times 1 plus 2 plus 0 minus 2, all over 2, which gives us a final value of 0. Hence, we can conclude that the molecule has 0 degrees of unsaturation. Let's move on to the next question. Calculate the degrees of unsaturation for the following molecules given the molecular structure. Once again, feel free to pause the video and try these problems on your own first. For trans-2-butene, we can use the degrees of unsaturation formula, but there is an easier shortcut. Notice that the molecule is a hydrocarbon with 1 carbon-carbon double bond. This, along with its name ending with En, indicates that this molecule is an alkene and hence has 1 degree of unsaturation. For pyrrole, we can also use the degrees of unsaturation formula, but again, there is an easier shortcut. Pyrrole is a ring structure with 2 double bonds, meaning it has 3 degrees of unsaturation. For transenamic acid, we can once again use either the equation or the shortcut to find its degrees of unsaturation. Transenamic acid has a benzene ring in the molecule, which we know has 4 degrees of unsaturation because benzene is a ring structure with 3 double bonds. There are also 2 more separate double bonds in the molecule, the carbon-carbon double bond in the alkene and the carbon-oxygen double bond in the carbonyl group. These 2 double bonds each contribute 1 more degree of unsaturation each, so in total, transenamic acid has 6 degrees of unsaturation. Finally, for hexane, we notice that the molecule is a hydrocarbon with no multiple bonds or rings. This, along with its name ending in ane, indicates this molecule is an alkane and fully saturated with 0 degrees of unsaturation.